So we can start our lecture today. I want to take the content we discussed last time, and in particular we are talking about this kind of system. The system consists of an airfoil like this, and
Professore, non sta condividendo, credo.
yes, just a second. I did, but okay. Okay, so the system is composed by section airfoil. This section airfoil is, in general, is also known as typical section in the sense that we have an aircraft with a wing. So this is our aircraft, and we have in mind a very representative and special section of such a wing. Oh, excuse me. I'm sorry. Okay. So we are considering a very special section like this of this wing, and this section here is also known as typical section. And this can be considered as the most simplified model for representing inelastic behavior. And therefore, if you consider this wing as elastically connected to a ground, like here, you have this stiffness, vertical spring, and you have also this torsional spring right here, and these two springs are located in this point here, and the coordinate of this point is xe, and E is for elastic center. As you know, in particular, people coming from an aeronautical master degree, this elastic center is a very special characteristic of the section. This is a section, a structural section of your wing, and these are spars, web, and these are stringer. And so if you consider your section as composed by sub-elements like this, stringer, spars, and web like this, web, And you have a special point known as elastic center here. And this point is a point such that if you apply here a concentrated force, the effect of a vertical concentrated force as applied in this point gives as a result a pure translation of the wing section like this. Only translation. Only vertical translation. And this is just equivalently happening here, because if this point now is the point where the springs are connected, if you apply a static force in this point, the result is a translation, a pure translation of this section airfoil. So the role of this point in the 2D vision is the same role here in the 3D vision in terms of elastic center. Okay? And after this parallel similitude, we have that this h degree of freedom is actually representing in the 2D vision the role of bending motion you have in 3D vision. And the role of alpha, degree of freedom, which is actually this angle here, we have alpha and we have h. We have two state space variable like h and alpha, function of time. This is our state space vector. So the role of alpha is the equivalent of bending. The role of, of h is the role of bending. The role of alpha as the role of torsion angle. And so we have okay, perfect. And so we have alpha as torsion and h as bending. And this in the 2D vision, and here in 3D effective vision. Okay? Okay. So this is a typical section. And therefore, when we define this quantity as the ratio between K, H, which is the spring parameters associated to the vertical spring, divided by M, which is the mass per unit length. This ratio is something representing the frequency, better the square of radiance frequency, but this frequency is not properly the natural frequency of the system. This should be the natural frequency of the system in the case the bending and the torsion mode were decoupled. So we have two frequencies, this and this. Also we have another frequency like omega square alpha, and this is the ratio between K alpha, which is the stiffness of the rotational spring, and J alpha, which is the moment of inertia of the section per unit length, again. This unit length is the span length, wingspan direction. Wingspan. And this moment of inertia per unit length with respect to the elastic center. Please, attention. Okay, so we have these two quantities which are actually representing two frequencies, but they are not, please take this note, they are not the natural frequency of the system. We will consider this comment later. They are not the system natural frequency. Dot, 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 dot. See later for this comment. Okay, so we have this 2 degrees of freedom concentrated, mass concentrated and stiffened concentrated system, 2 degrees of freedom mechanical system. This mechanical system, in our opinion, is representative of the wing dynamics in a special section. For this system, this mechanical system is also known as typical section. And the characteristic parameter of this typical section are the spring parameter, K alpha, KH. We have also two parameters, the mass per unit length and the moment of inertia per unit length with respect to the elastic center here. And finally, we have the final two parameters, which are the coordinate of the center of mass here, and the coordinate of this point here, where the two springs are connected to the airfoil. This point was qualified as the elastic center because in the similar way as in an effective wing, if you apply the static force here, the effect of this application of this force is just a vertical translation, not rotation. Okay? Very simple. Very last point, we are defining as state space variable h and alpha. H is the vertical displacement of this point here, which is 1/4 chord position, and the chord length is equal to C, which is equal to 2B. B is the half chord, look. And the total length of the chord is C. Okay? And that's all for the description of the system. And after this geometrical detailed description, the past time we have obtained these two equations in this way. First we express the total elastic energy and the total kinetic energy here. So the total elastic energy, you have these notes. You don't have to write nothing. You already have this. So this is the node. This is the coordinate of the elastic center. This here is u in the x e point in any time, and since u, we decide that the displacement u as a function of x and time is equal to h plus x by alpha. And if you want to consider the displacement of the elastic center, you have just to put xe instead of x here. And therefore, we have this for representing u in the elastic center. And so the total elastic energy is the elastic energy stored by the kh spring, which is 1/2 kh by ue to the power 2 plus 1/2 k alpha by alpha to the power 2. And this is the elastic energy. For the total kinetic energy, we have to, this is the kinetic energy, total kinetic. And here we have h dot plus alpha dot xg, because again, this part here is u dot in xg, so the velocity of the center of mass. And therefore, the kinetic energy is 1/2 m mass per unit led by the velocity of the the center of mass to the power 2, plus we have the contribution of the rotational degree of freedom, so multiplying 1/2 alpha dot h alpha dot to the power 2. And pay attention, this is not j alpha, this is jg, this is the principal moment of inertia. In particular, you know by the Huygens relationship that if you want a moment of inertia with respect to the elastic center, this is equal to the minimum moment of inertia, which is the moment of inertia with respect to the center of mass, plus the mass by the offset between the elastic center and the center of gravity. And this is the distance between E and G, the distance to the power 2. Okay, so this is the relationship between this JG and J alpha. I have introduced it here. Okay, so we have applied straightforward the Lagrange equation motion, and then we have derived the kinetic energy with respect to h dot, so obtaining this quantity, and this quantity has to be derived one time by the time again, and so obtaining this final relationship. And then we did the same for this quantity, so obtaining this, and finally we did the same with the elastic energy, first deriving with respect to kh here, and then deriving with respect to alpha. So deriving with respect to alpha, we have kh again by k by alpha plus xe alpha by the derivative of this with respect to alpha, so xe, and then we have k alpha by alpha. Okay, so this is the result of this derivative, and at the end we can apply the Lagrange equation of motion, and then we have this system And with this mass matrix and this stiffness matrix, as you can see, this mass stiffness matrix are symmetric, as you expect, and they are also positive or semi-definite positive for the stiffness, and correspondingly to this H and alpha degree of freedom, you have the generalized force EH and E alpha as forcing term in your equation. These two terms here, okay? Forcing term. Now, consider the general theory we have developed for this Lagrange equation of motion, and in this general theory we have that the displacement is equal to this shape function, this trivial shape function multiplied by our generalized coordinate plus another shape function x by, excuse me, this x by this other generalized function. So this is psi1 shape function, and this is psi2 shape function. And therefore, if you have for your airfoil if you have for your airfoil a surface, a load per unit surface like T, just surrounding your airfoil, and this is the physical load you have. Your generalized force are such that the EH, by definition, is equal to a surface integral, but the surface integral is now a circuit integral around the airfoil of your generalized force, this vector, which is the pressure distribution vector, projected on your shape function. But your shape function is just this function with equal to 1, okay? And it is actually a vertical constant vector, vectorial vector, just a vertical vector like k because this frame of reference, you have x and you have k in vertical direction here, and therefore we have the following. We have that this vectorial shape function 1 is something like k by 1. And so we have dot psi 1, okay, ds. But in the case, look this point, please, pay attention. In this case, we have that this force is the pressure force, okay, and the pressure force are minus pressure by n, the normal, dot kappa ds. And look to this typical approximation for thin airfoil. Means that we have from this situation to this situation x zeta, we have that this integral is actually equal to an integral on the line in dx only, not around, but just a line integral from here to here, trailing edge, leading edge. So better write x leading edge to x trailing edge in dx. And for each x point, for each generic x point, you have what you already have up and down, this normal and this normal. This airfoil collapsed in a line. This open, excuse me, this closest surface is collapsed to a line, as you know, remember, and therefore, in the old vision of the in the old and correct vision of your circulatory integral, you reduce it to a line integral, but for each point you have to consider up and down in the same time, and therefore we have to consider minus P upper minus pressure lower n, and this n now is the unique normal in the upper side, and that's it. This is n as the unique normal in the upper side, and writing upper minus lower, you are considering in one shot upper and lower point in the same x, in the same x coordinate. Okay, and therefore we have that the old circulatory integral is now almost equal to, for a thin airfoil, is equal to a line integral from the leading edge to the trailing edge, and this scalar quantity, look, between n dot kappa is equal to 1, because for thin airfoil in the undeformed configuration, this product is practically equal to 1, because the normal is a unit vector and the k vector in zeta direction is a unit vector again. And at the end of this story, we have, excuse me, okay, we have that another point, and excuse me, but remember that our positive direction for h is down. I'm sorry. So this is the direction of the z-axis, excuse me. So h, look here, is down, and therefore zeta direction is downward, and therefore, I'm sorry for this, we have we have here that this product is not equal to 1, but it's equal to -1. Okay? And so we have that the generalized coordinate is equal to the integral from the leading edge x coordinate and the trailing edge x coordinate of P upper, pressure in the upper side, minus pressure in the lower side, in dx. Okay? And for this reason, this quantity, what is representing at the moment? This quantity is representing as generalized force, H, EH, the lift on our airfoil, but in particular as a generalized force associated to this generalized displacement. This is not properly the lift, but it is minus the lift. Okay? In fact, we have the integral of pressure upper minus pressure lower, not the contrary. Okay? So this is very interesting because we have a rigid body elastically connected to the ground, representing this elastic typical section, but we have consistently a rigid body with a small displacement. So the motion of this rigid body is linearized motion. And this linearized motion, we have this equation, these two equations, and the generalized force associated to this equation can be obtained by the physical force. The physical force is a time-by-time pressure distribution given by the vector t in any time. But the forcing term you have to write here is not your original physical vector, but following the Lagrange equation of motion theory, this generalized force is the projection of this physical vector onto the corresponding mold shape. So when you project this physical load on our first mold shape, psi1, we have the lift. Okay? Better, we have minus the lift, because we have chosen as shape function a downward shape function, because we have considered as degree of freedom a displacement positive when directed down. Okay? And finally, we can also obtain as a second generalized variable H alpha. And what about this H alpha? By definition, H alpha is the projection of T physical pressure distribution vector by the mode shape. But the mode shape is K X now as psi 2 vector function. Okay, we have to consider this projection in ds first, then we can substitute the physical pressure distribution. So we have minus P and dot K X ds, but because of the thin airfoil hypothesis here, we have that this circuit integral is equal to a line x integral from the leading edge to the trailing edge, and we have P upper minus P lower again, and dot K X dx. This dot product is minus 1, and then we have that this second generalized force is actually the integral from the leading edge to the trailing edge of P upper minus P lower x in the x. And this is actually a moment of the aerodynamic force with respect to this point here. We have the moment with respect to this point here, the point of where we have defined the vertical displacement, which is actually the origin of our x-axis. Okay? The origin of our x-axis. So this is the origin of our x-axis. The distance from this point and the leading edge is 1/2 the half chord, so 1/4 the chord, and so the distance between this point and the trailing edge here is 3/4 the chord. Okay, so this is the leading edge, the trailing edge. Okay, and so we have this. So this is the moment, the aerodynamic moment, aerodynamic. Why aerodynamic? Because this moment is due to the pressure distribution. So this is the aerodynamic moment with respect to 1/4 of chord, which is the origin of our axis. Now, a question for you guys as a student in aerodynamics. Do you know the amount of this aerodynamic moment in the case of static aerodynamic and in the case of straight thin airfoil? Do you know? What about the aerodynamic moment of an airfoil with respect 1/4 of chord? For a straight airfoil, not this, but a very thin airfoil, and with no curvature, so a straight and thin airfoil. What about the aerodynamic moment with respect to this characteristic point? Silence. Silence. Is anybody there? Does this lecture make sense or not? Is anybody? Hello?
Yes, Professor.
Are you there? Okay. Okay. Was there any problem in the connection? Because I'm not realizing any kind of problem, but I don't know if this is true. Do we have any problem on the connection? What was busy again? Busy? Okay, so let me do my last 5 minutes of lecture. I wanted to dedicate this hour of lesson for you on this practical issue by describing this kind of system, which is a very standard system in elasticity, representing in the simplest way, the dynamic of a wing and the elasticity of a wing. Okay, this is almost an analytic model for you. Okay, so I decided to dedicate this time for describing this model, and I hope to have convinced to you that the Lagrange equation of motion are actual mean for describing the dynamic of the wing in a simple way. However, we discussed the generalized force, the meaning of these two generalized force. We have a moment for this, we have a lift for this, but this moment is now representing the moment of the aerodynamic load distribution with respect to 1/4 of chord. And this moment, if you consider the standard linearized aerodynamic theory, is for a straight airfoil is identically equal to 0 for steady. For the moment of the aerodynamic moment around an airfoil with respect to 1/4 of chord is 0 if you consider the steady theory. but we are considering the unsteady one. So I expect to be not completely zero in my analytic theory. Okay, so this is just a comment. However, now we have at the moment this final system, okay, and the final system is composed by these two matrix and by this this mass, stiffness, and load, or forcing term. Okay. Now, what about the mode of vibration of this system? Mode of vibration of this system. And natural frequency. Okay? Cis. We have a couple of mode and a couple of natural frequency. We have the following system as M applied to H alpha plus K applied to H alpha. We have 2 by 2 matrix, 2 by 2 matrix, and we have a load vector given by the aerodynamic. But in the case of free response, we have 0 here, and the mode of vibration are obtained by solving the determinant of k minus omega n to the power 2 m is equal to 0. And therefore, we should have, by developing this determinant, we should have something like omega n to the power 4 plus a coefficient omega n to the power 3 plus a coefficient obtained by developing the determinant omega n to the power 1, and finally a final coefficient equal to 0. These three coefficients, this, and this, depend on M matrix and K matrix elements, of course. Solving this equation, you have omega 1 and omega 2 as positive quantity, as you know very well, equal to something, equal to something. These two are the natural frequency, and this natural frequency are not equal, the first one to this quantity and the other one to this other quantity. But you could have this quantity in the case, for example, in the case you have this xg center equal to this xe center collapsing. Okay. In fact, in this case, you have that this matrix, when you have these two quantity cancel, if you have xg equal to xe equal to 0, and you have in this case jg equal to j alpha. In this very special case, you have that these two mass stiffness matrix will be diagonal. So in this case, you have this quantity collapsing equal to 0, and this is collapsing, this is collapsing, this is collapsing. And again, this term is collapsing, and this term is collapsing. And at the end, if you develop this, excuse me, if you develop, in this case, this determinant, in this case, omega 1 is equal to omega h, which is equal to kh by m, and omega 2 is equal to omega alpha equal to square Ka alpha by Jg. Okay, so this can be defined like the bending and torsional natural frequency of the dynamically uncoupled system. Uncoupled in the sense of torsion and bending. When you have the elastic center, which is the same point of the mass center, and is representing, and you are representing the vertical displacement of such a special point, only in this case, the bending is uncoupled with respect to the torsion. Okay? So these two special frequencies, omega h and omega alpha, are not the natural frequency of the system, but are the natural frequency of the uncoupled dynamical system. Okay? Okay. Straightforwardly, we can undimensionalize the system. Next final step are make the equations undimensional and introduce suitable undimensional group for characterizing our system. Okay, and we will do this next time, the day after tomorrow in the afternoon. And thank you for your attention. For Esther Batsida, Vz was representing a vertical external load. Yes, I will.
Okay,
I will upgrade my whiteboards whenever possible. Okay.